Okay, let's look at the kinetic molecular theory of gases then. So here we go. The kinetic molecular theory. Cha-ching. Okay, of gases. Okay. Basically what we're going to look at here is we're going to look at a box of gas, and we are going to assume that this gas is moving at a variety of random speeds and directions. And what we're going to look at here is we're going to try to figure out, can we figure out the average velocity of this gas? Because if we can do that, we know that temperature is nothing more than the average kinetic energy, and kinetic energy is 1/2 mv squared, dealing with velocity. So if we can find this average velocity, we have this average kinetic energy, and if we have this average kinetic energy, that in a way can get us to a temperature. Okay. Now it's important before we begin the kinetic molecular theory of gases to think back to our wonderful friends in chemistry, to this classic equation, PIVNERT, PV equals nRT, or as some people like to write it, nKT, depending on if you like to talk about moles of something or the number of molecules. I always made a mistake growing up in chemistry where I'd call moles MOLE and I'd call molecules MOLE, because that's how I just abbreviate everything, so I got confused all the time. But essentially, we're going to be using some PIVNERT ideas here, looking at ideal gases, and applying these to just a kind of more physics application than you've done in chemistry before. Before we begin, there are a few assumptions that we need to make about our gas in question. The first assumption is that we are going to have a large number, let's zoom in here, we're going to have a large number of molecules of some mass m, it doesn't matter what it is, and all of these things are moving in a random speed and direction. So we don't just have one of these, we just don't have like two of these, we've got a slew of them, just like a ton, okay? So because we've just got a ton of these things, we can say they're all random speeds and directions, and we can start applying some statistical ideas to them at some point. And yeah, when in doubt, like PIVNERT, right? That's the standard go-to. We're also going to assume for this that the molecules are far apart. Okay, so they're not like a solid in some sort of like crystal lattice structure where we're looking at vibrational modes or anything like that. It's just there's a molecule over there and there's one over there too, and they're just chilling and doing their thing. Okay? We need to assume that classical mechanics, that's like all the Newtonian stuff we did last year with kinematics and F equals ma and impulse momentum, we're going to assume that all still applies. How you doing, N2? So classical mechanics with momentum still applies. Yes, I realize we're at some small micro level where, if you get down to the nitty gritty, we can say, what about these? Stop. We're just going through this as the classical mechanics version of it, okay? And Druin's in here. So we've got classical mechanics, and specifically, we're going to be looking at momentum. And hopefully you remember momentum as P equals mv. So momentum is a mass times a velocity. And last but not least, whew, so many assumptions, we're going to assume that all collisions are perfectly elastic. Okay, so if something bounces off of something else, such as a wall, then it doesn't lose any energy. All the energy is contained in the system. It's a perfect setup. Okay, so those are our 4 assumptions we have to make at the start of this, and we're going to be using and abusing PV equals nRT or NKT as we go through. So let's start with what we need. First, I have a box. Let's just create a box out of magical thin air, as we often do in the world of physics. It's a perfect box. There's nothing wrong with it. I drew it perfectly as always. And let's just pretend for a second that we are going to look at exactly one molecule in here moving at some random speed and a possible random direction. So it's just like, whoop, it's moving with some velocity. Okay? We're going to give this box side length of L. It just has some length to it. It's a perfect cube, so all the side lengths are L. Its volume is L cubed. That's what we have in our box. Okay, and we're just looking at one molecule right now. Yes, we have a large number of them, but right now we're just looking at one. Now, if I have this one molecule here, when it undergoes a collision, we're going to see the following. When this molecule bumps into the sidewall of our container, okay, and we're going to assume that it just bumps in perfectly square, so maybe it's a slightly better idea to draw this arrow going directly to the left or right. If this molecule bumps in perfectly square with the wall, it's going to strike the wall, boink, and then it's going to move back in the opposite direction at the exact same speed, because we claimed that these collisions are perfectly elastic. And we just got a huge thunderstorm here. Holy cow, how random is that? Look at this. Look at this storm. Piglet's gonna start bailing. Okay, so there we go. So we got this perfectly elastic collision. Whatever velocity it had coming in, it has the same speed as that coming out, but it's just a new direction. So what this means, if we think about our change in momentum, is that the change in momentum we have is equal to the mass times the change in velocity. Okay? Now, one of the things we need to remember is that since this came in with some velocity, let's give it a value of 4 meters per second. It technically came out the other direction, so this is like a negative 4 meters per second. The difference between those is not 4, the difference between those is 8. The direction changed, so we get this flip of the sign. So what we can actually say here is that because this is going and it's changing direction, our change in momentum here is actually 2 times the mass of the molecule multiplied by that initial velocity we had. And since we're just talking about the left and right here for one molecule at the moment, let's just call this the x velocity, because this object is moving directly to the left or directly to the right. Yeah, if we tick the box, we could call it y, or if we tick the box, we can call it z, but at the moment, let's just call it the x velocity, okay, at some x speed. Now, we can also work out the amount of time it takes this object to move and bounce back and forth on the box. If we just think about the fact that a velocity is some sort of displacement over a time, then that means a time is the displacement over a velocity. So time is like how far you've traveled divided by some velocity. Well, in our case here, the distance you've traveled is to go back and forth across the box 2L over whatever velocity you have in the x direction. So that equals time there. Okay, so these two ideas right here are very important for us just to start out with. Okay, so we've got these nice elastic collisions. From here, and if we think about classic Newtonian mechanics, we might remember that Newton actually related momentum to the classic F equals ma, Newton's second law. Newton actually did this with momentum. We later on said, yeah, momentum's great, but we kind of teach it as F equals ma, looking at forces accelerating objects. But what we can do here is if we do go back to that classic F equals ma, we can say that some force acting on an object is equal to a mass times an acceleration. And we hopefully remember that an acceleration is nothing more than a change of velocity in some amount of time. Well, if we are changing a velocity and multiplying it by a mass, like right here, we already have done that. That was our momentum. So what we can do is we can take this momentum idea and we can say that 2mvx, our equation from above right here, divided by time is equal to the amount of force being applied to this object. Okay? And since we know the time here is 2L over Vx, we can say that 2mvx over the time, which is 2L over Vx, equals some amount of force we're placing on an object. Whew! If we do a little bit of canceling stuff out, or dividing the terms out, as the great Cotton would like to say, our 2's go away, and our Vx is going to double that up, so we're going to get a square value. So what we end up getting over here is that the force acting on some molecule is equal to mvx squared over L, the length of our container there. Okay. Well, this was for a single direction. That's just the x-axis. And we don't just have the x-axis here. We go the x-axis, we go the y-axis, we go the z-axis. You've got everything going on. So what can we do here to kind of incorporate everything into one neat little package? Well, since we have, one of our initial assumptions was that there are a large number of molecules, all of the same mass, moving in random speeds at random directions. Since we can assume there's so many at random directions that just as many are in the x direction as in the y direction, as in the z direction, as in somewhere in between. And we could do this as the classic like triple integral and whatnot. But what we can also do is we can just kind of create a statistical average because we've assumed large numbers here. What we can do is we can say that if we have some average velocity, I'm going to call this v bar here, okay? Some average velocity v bar here could be thought of as the square root, that didn't carry, of the x direction value squared plus the y direction value squared plus the z direction value squared. And these values for the y and z are the exact same as Vx because, as N2 is pointing out, we're just abusing symmetry here. Something is just as probable to move in the x direction as it is in the y direction. So if we wanted to go back up through what we've done so far and change all of these Vx's to Vy's and redo it again, we could. If we wanted to go back and call them all Vz's, we could. There's just as probable for anything to do that. So that's kind of what we're doing there. And that gives us this idea of what's going on there. Okay, so we're just taking this idea of symmetry and using it in that way. Now, if we take the square of each side, then that gets rid of our square root. So we end up seeing that some average squared is just Vx squared plus Vy squared plus Vz squared. Okay, so we have all of these averages here just like that. Which, if all of these are really just the same in theory, because it's just as probable for anything to happen, what we could say here is this is just equal to 3 Vx squared. Okay? So our equation for our force, m and then Vx squared over L, it's going to change slightly here. We're going to have instead that this is... Oh, it's really coming down. Some mass over the length again, because that's our m over L term right here. And then this Vx squared needs to happen in all directions and for all particles. So since we have some large number of particles, because remember, this was a single direction and a single molecule. Since we have some large number of molecules here that we need to do this for, okay, I'll call that capital N, just like we have up here in PivNert. I'll say m over L times some large number of molecules N bad weather times this value here, because this would be like times the average velocity squared, but we know that average velocity is just 3 times whatever Vx squared is based on that symmetry. So we can get this equation m over L N times 3 Vx squared. Okay? I should note out, technically, whenever we found these terms in here, what we actually did is we found the average of all of the molecules moving in the x direction, which was that this would be like Vx squared in a direction on average, so that's V bar. That's equal to the addition of all of the molecules moving in the x direction squared divided by the number of molecules. That's technically what we did to get those values here. So these are all technically V bars. Just kind of ignored that for a second. It's technically there. That's a very bad sigma. But I kind of hand-waved that one into existence. So if you want a formal proof that that technically is the average in all the x directions, so I'm taking averages and finding averages. But in the end, I get this equation down here, and that's kind of where we're at right now. Whew. Okay. Or did I mess that up? Oh, I did. Whoops. Boo. It's over 3. It's over 3. The reason why it's over 3 is that if V bar squared equals 3 Vx squared, then that means V bar squared over 3 equals Vx bar squared. And since I said this was a 3x bar squared, then that's over 3. Okay? And I'm going to leave this as general velocity there. Right? Or did I just ignore my own conventions? Yeah, because this was originally Vx squared up here, so I had to divide it by 3 in order to get the V bar in there. Okay, so this right here, this is a good equation where we are at. Okay, I originally had, this is actually Vx squared there. In order to get V in there, I had to divide by 3 in order to replace that Vx squared. Okay, whew. Math. It's been a long day. Okay. Now that we've got this equation, and remember all of that was just equal to force acting on some particle. Let's just rewrite that out again, make life a little bit neater. F equals m over L times the number of molecules times the average velocity of all the particles in any given direction squared divided by 3, so we can get rid of the Vx factor. Let's go back to pressure. because pressure is just like whatever. L in this case, right here, is the length of a cube that these molecules are sitting in, right here. So if you're looking for what is L, L is some length of the cube that these objects are moving through, because we needed that length in order to get a time of how long it takes to move back and forth. So we have the mass of the molecules, the length at which they travel through across the container before they run into a collision, the number of molecules we have, the average velocity in any given direction squared so that we get positive numbers, divided by 3 so that we look at all directions and not just the x-axis, and to get rid of that Vx we were looking at before. This is what we have. Whew! Yay! And now, almost out of nowhere, we think of pressure. Because if we think about putting gases into a container like a box or a can, then we have some sort of pressure that can build up in there. If we change that temperature, you think of a can of beans you put on a fire, it'll explode. We know there's some pressure in that container. And this starts to bring us all the way back to these Pivnert's idea. Like, hey, look, a pressure times volume equals nRT. So since that has to do with ideal gases, and we're talking about gases, and there's a fixed amount of gas in this container, why don't we go back to pressure and see if we can do something there? Well, from pressure, as we've seen, pressure is some force over some area. And if we take our previous equation, that m over L times n times v bar squared over 3, we can take this as, and I'm gonna break some stuff out. Here's our 1/3, so that's the over 3, times n times m, so there's n and m, times v bar squared over, and then here's our cross-sectional area A, and then here's our L that bops in right there, multiplied together. Woo! Now, previously when we were doing fluids, we saw that if you have a cross-sectional area A, and you stack a bunch of these on top of each other, just like sheets of paper, you start building yourself a volume. So a cross-sectional area times some length ends up giving us a volume. NmV bar squared over V. And this is nice because now I've got a pressure and a volume, and I'm starting to see where Pivnert went. So I'm just going to bounce this volume over to the other side. Multiplying volumes to the other side gives me PV equals 1/3 NmV bar squared. Okay? Now, if I'm looking at this, there is something there that I'm starting to kind of see. And it takes a little bit of like luck and a little bit of intuition to kind of see this come to life. I've got this mv squared term just here in existence. And I know there's other physics equations that use this mv squared. Specifically, kinetic energy. Kinetic energy is 1/2 mv squared. If only I could get it so that I could put a 1/2 there, and that would become kinetic energy, this would be nice and easy for us. Well, what we can do here is we can recognize this. If we take this idea of 1/3 and break it into 2 pieces here, we can take 1/3 and break it up. 1/3 is a combination of 2/3 times 1/2. That equals 2 over 6. Multiply your numerator, multiply your denominator. 2 times 1 is 2, 3 times 2 is 6. And that does equal 1/3. Well, that 1/2 is what I need for kinetic energy. So what I can say here is that by breaking up the 1/3, I can say, hey, 2/3 times n times 1/2 mv v bar squared, because 1/2 times 2/3 gives me 1/3. That has to equal PV. And this 1/2 mv squared, that's really nice for me. That gives me some idea of a kinetic energy going on here. So what we can start looking at here is, okay, can I do something with this combining kinetic energy and combining other factors? Well, let's just break this up and move it around a little bit, and kind of rearrange it. If I take PV over N, that would equal 2/3 times 1/2 m v bar squared. That's our kinetic energy that we're carrying around. But I also know what PV over N is. PV equals NR, excuse me, not nRT, NKT, the Boltzmann constant. Which means that if I have PV over N, that must equal KT. Because of this, I can say that, if I move my 2/3 to the other side, I can say that 1/2 mv squared equals 3/2 KT, which means that the kinetic energy is equal to 3/2 KT, where K is Boltzmann's constant, and this equals 1/2 m v bar squared, just like I had right above it. Because of this, if I move some stuff around and I solve for velocity, we see that this average velocity squared here is going to equal 3kT over m. And this velocity here, it was an average velocity taken over all different directions, and if I'd like to find it, I could take the square root of each side. When I do this, what I'm actually taking is something known as the root mean squared velocity. It's a root here. It's the mean, meaning the sum average of all given directions, and those values were squared such that we only have positive values here. So this is what's known as an RMS, a root mean squared, and that gives us some average velocity of the molecules in our container. So if you picked out some molecule at random, or if you took the average of the entire system, the average of the entire system would be this RMS velocity, and it would be totally dependent on the temperature of that gas and the mass of the molecules that you were looking at there. Okay, so this RMS velocity is going to be super duper important for us, as well as this idea that the kinetic energy of that gas is equal to 3/2 kT. Okay, so these are two huge equations for us for the kinetic molecular theory of matter for ideal gases. And that's how we derived them. It was this very long process where we had to make a ton of assumptions, and we had to go through just a lot of math in order to get it. But by basically using the conservation of momentum, looking through times, applying forces, applying pressures, knowing Pivnert, and coming up with a few little like, hey, look, 2/3 and a half make 1/3, we created this little law right here for us. So it's a nice thing to have in your pocketbook whenever we're discussing ideal gases and looking at energies within them. So that's how we do that. That's finished.